Welcome to The Explainer. Today, we're stepping into the invisible, highly energetic, and honestly, kind of violent forensic world of mass spectrometry. If you've ever wondered how analytical chemists actually identify unknown compounds, well, the answer lies in destruction. We're going to learn how to reverse engineer molecular victims by analyzing exactly how they fall apart.
So think about this. What really happens when you blast a molecule with high-energy electrons? You'd probably imagine complete explosive chaos, right? But that's the secret of mass spectrometry. The molecule absorbs a massive amount of energy and shatters, absolutely. But it doesn't shatter randomly. It creates this highly predictable shatter pattern, governed by some pretty strict chemical rules.
Here's our roadmap for today's explainer. First, the molecular puzzle. Second, Stephenson's rule of stability. Third, one-bond cleavage mechanisms. Fourth, two-bond snaps and eliminations. Fifth, the Michel-Faraday rearrangement. And finally, decoding the mass spectrum. Let's get into it.
Okay, Section 1, the molecular puzzle.
Scientists have been cracking these molecular puzzles for over a century. The foundational principles literally date all the way back to the 1890s with J.J. Thomson. He actually won a Nobel Prize for his efforts in 1906. By 1918, A.J. Dumpster built the earliest modern mass spectrometer. And the field, it's just accelerated since then, leading to major breakthroughs, like Fred Michel-Farady's famous rearrangement in 1956.
So the game always begins with the initial ionization event. Picture this. In the ionization chamber, a collision with electrons strips exactly one electron away from our sample molecule, and that leaves behind a radical cation. Now that's a molecule with an odd number of electrons and a positive charge. This radical cation is our starting point. Because it just absorbed all that extra energy from the collision, it's in a highly excited vibrational state. It's vibrating so intensely that it simply has to break apart.
Moving on to Section 2, Stephenson's rule of stability.
Think of this kind of like dropping a complex glass object on a hard floor. It doesn't just vaporize, right? It breaks at its weakest joints into the most structurally stable pieces. Stephenson's rule tells us that the most probable fragmentation is the one that leaves the positive charge on the fragment with the lowest ionization energy. To put that in simpler terms, the fragmentation pathways that lead to more stable ions, those are always going to be favored.
The source material actually puts it perfectly. The ununimolecular processes that are energetically most favorable give rise to the most fragment ions. If you're fresh on your organic chemistry, this should sound incredibly familiar. It perfectly mirrors Markovnikov's rule. Just like in chemical reactions in a flask, the most stable carbocation wins out, even in the vacuum of a mass spectrometer.
All right, Section 3, one-bond cleavage mechanisms. There are two dominant ways a single bond can snap. The first is radical site-initiated, or alpha cleavage. Now this one can be slightly confusing. The bond that breaks isn't the one directly attached to the radical site. Actually, scratch that. It's the bond to the next neighboring atom that snaps. The other mechanism is charge site-initiated, which is also known as inductive cleavage. This happens when a highly electronegative heteroatom plays a game of tug-of-war, literally pulling an electron pair toward itself and causing the bond to snap. We can actually see this one-bond cleavage in action right here, looking at the mass spectrum of butane. The molecular weight of butane is 58, but notice how tiny that peak is way over on the far right. Instead, we see this absolutely massive, dominant peak at an MZ of 43. This is the direct result of a single bond snapping, losing a methyl radical and creating a highly stable propyl cation. It's literally Stephenson's rule unfolding right before our eyes.
Next up, Section 4, two-bond snaps and eliminations.
Now, two-bond cleavages are fascinating because they occur via an elimination process. The odd electron molecular ion breaks down and yields a new odd electron ion, but in the process it ejects an even electron neutral fragment. We're talking things like water, a hydrogen halide, or an alkene. Because this ejected fragment has absolutely no electrical charge, the mass spectrometer's detector can't see it. It leaves behind a ghost. We can only deduce what was lost by looking at the missing mass between our parent ion and our new fragment ion.
One of the most spectacular two-bond acrobatic moves is the retro-Diels-Alder fragmentation. If you have an unsaturated six-membered ring, like a cyclohexene derivative, it can practically unzip itself. It breaks apart to produce the radical cation of a diene and a neutral alkene. And, perfectly obeying Stephenson's rule, the unpaired electron and the positive charge stay right there with the dying fragment.
Take cyclohexanone, for example. Cyclic compounds don't just snap in half. They undergo these complex eliminations that create highly distinctive scatter patterns. You can clearly see these dominant fragment peaks at 55 and 42 here. Those are pointing directly to the structural acrobatics happening as the ring opens up and those neutral fragments are ejected.
Which brings us to Section 5, the McLafferty rearrangement.
In the McLafferty rearrangement, a gamma hydrogen, so that's a hydrogen on a carbon 3 atoms away from a radical cation like a carbonyl, transfers to the charge site through a 6-membered transition state. At the exact same time, the sigma bond between the alpha and beta positions snaps. This beautiful, highly coordinated dance results in a brand new radical cation and a neutral alkene.
44. I really want you to remember this number. In the mass spectrum of valoraldehyde, 44 is the exact m/z value of the base peak. Why? Well, because that fragment is the direct result of a McLafferty rearrangement. Seeing an intense peak at 44 is a massive forensic clue that you are looking at an aldehyde with a chain of at least 3 carbons attached to the carbonyl. It's a real game changer when you're looking at a spectrum.
Finally, Section 6, decoding the mass spectrum.
Let's look at this spectrum of 2-butanone. We've got a carbonyl group with a methyl on one side and an ethyl on the other. Through alpha cleavage, it can lose either one. But look at the data. The loss of the larger ethyl group creates a massive acylium ion peak at 43. Meanwhile, the loss of the smaller methyl group creates a much smaller peak at 57. This proves Stephenson's rule in action. The molecule preferentially loses the larger alkyl group because it leads to a more favorable, stable fragmentation pathway.
So the crucial takeaway here is that you need a systematic approach, a kind of forensic checklist. First, you inspect the molecular ion cluster. Then, look at the high mass peaks and determine if the mass losses are odd or even. Odd mass losses usually point to simple, homolytic single-bond cleavages. Even mass losses, those are the ghostly fingerprints of rearrangements and eliminations, like our good friend the McLafferty rearrangement. Finally, you scan for distinct structural fragments. Now, why does this all matter? Because these aren't just abstract textbook rules. This is literally the toolkit every analytical chemist uses to identify unknown substances in the real world.
Which leaves us with this final thought. We started by picturing high-energy electron collisions as just total chaos. But knowing these predictable, mathematically precise rules of destruction, how will you now look at the elegant, hidden order inside a mass spectrometer? Even when breaking a molecule completely apart, science finds a beautiful, readable logic. Thank you so much for joining me in this explainer, and keep looking for the structure inside the chaos.